Hi everyone, and welcome to the physics class for Medics Online. So everyone, thank you for coming on a Sunday, and hi to everyone who says hi. So what we're going through today is atoms and nuclear radiation. Now this is a topic that we talked about last month for whoever was here last month, and we're going to expand on what we already know. So we're going to go through some revision of what we learned, and we're going to expand on that a little bit and focus on some different topics this time. All right, so some of the topics that we're going to cover is radioactive decay and nuclear radiation, then nuclear equations and half-lives, and then nuclear fission and fusion. So some of these are completely new, so these you would have already seen before. So these would be some of the key learning objectives that we want to cover today, and I'm always going to come back to this list and see, kind of check what we have already covered and so on. So starting with the atomic instability, because this is what leads to the decay that we want to talk about. So there are two different ways that an atom can become unstable. One of them is when it loses or gains an electron. So back when we talked about atomic structure, we know we've got our nucleus over here, and then there are electrons surrounding that nucleus. Now, when an atom loses or gains an electron, it becomes a so-called ion. Then the ion can be positively or negatively charged. And anything that is charged becomes reactive. It is attracted to the opposite charge. It wants to move. It becomes very reactive. And this is an important part in physics, but it's not the type of instability that we want to talk about today. What we want to focus on today is the radiation. So another way an atom can become unstable is that when a nucleus has an imbalanced number of protons and neutrons. So we know we've got protons, so these are the positive balls, and neutrons in the nucleus. And for the atom to be balanced, to be stable, there has to be a certain ratio between the number of protons and number of neutrons. When this is not right, it becomes imbalanced, and the nucleus itself tries to balance out this wrong number of protons or wrong number of neutrons. So it emits particles in form of radiation until it is stable. So for example, there are too many protons, the nucleus will try to get rid of protons. So it will be emitting these particles. If there are too many neutrons, it will try to get rid of these neutrons. And it will do this until it becomes stable. So these unstable atoms that are trying to change are called radioactive. And this process of getting rid of these particles is random. Now, this is an important thing to remember. It means we cannot quite predict it exactly. So we can estimate and stuff, but we cannot say at Tuesday, 15 p.m., this atom or this nucleus is going to decay. We cannot quite say that. All right. So let me just erase this little part so we can all see. So this process of an atom giving off radiation, so getting rid of some particles, is known as a radioactive decay. So this is a term that should sound familiar to you. Hopefully it does. And something about radioactive decay is that we can actually measure radioactivity. It's very important. We'll talk about why in a little bit. And one of the units that we can measure radioactivity in is Becquerel. So this is the BQ, that's over here. And as usual, these units are named after people who discovered something significant. So the Becquerel is named after Henry Becquerel, who first discovered evidence of radioactivity. So as a definition, the Becquerel is the count of the number of decays per second. So this picture right here, that is called the Geiger-Muller tube. And so what this does, so we would have radioactive gas coming in, and if there's any radioactivity, if there is some decay going on, this tube would sense it as a little pulse. So then if decay goes on, if a nucleus decays, we'll have a little pulse. All right, and that pulse is going to travel through these cables, and it's going to be seen here, and we can say, okay, there was a decay going on. And so this box tells us how many decays were there per second. So if there were 2 decays per second, we'll have 2 becquerels, and so on. If you go to the hospital, you might come across people who will wear badges that will look kind of like this, and we'll also might come across another picture, and these would be the so-called dosimeters. So these are important because either hospital staff or the nuclear power plant workers, but I don't suppose you would get here, they can be actually exposed to radiation. And so it's important for them to know how much radiation they were exposed, if any, and then act on it. So these badges actually measure radiation in so-called sieverts. The reason this is so important to measure and to know because the ionizing radiation damage to people can be cumulative. So if over time people are exposed to too much radiation, it can cause damage to the skin, even to organs or bones. We know that some kinds of radiation can cause cancer. So that's one of the reasons it is so important to monitor this. Now on to something that you guys would have seen are the 3 types of radiation. So we had the alpha radiation, beta, and gamma. You should always also be aware of the fact that beta, we have beta plus and minus, but we're just going to call it beta today. So with alpha radiation, remember we had 2 neutrons and 2 protons. So this is the same as the helium nucleus. All right, so alpha looks like this. This is the Greek letter for alpha. You can see it as this also. Now we have beta. Again, this is the Greek letter for it. And then gamma. Now, there is a significant difference between the 3. So, important thing that you should remember, alpha is a fairly big particle. It's a helium nucleus. So that would be right here. We've got 2 protons, the red ones, and 2 neutrons. When we look at beta, we would have a high-speed electron. So that means the new particle or the new nucleus has then 1 neutron less because it becomes a proton. So there's quite a lot actually going on behind the scenes of beta, but we'll have an electron ejected from this element. Now, these two both are particles, right? We've got the nucleus of a helium atom, and we've got an electron. What about gamma, though? So gamma is actually an electromagnetic radiation, and it is very high energy. And this actually, as it's not a particle being emitted from the nucleus, it would be always accompanying these two. So whenever alpha happens, or whenever beta happens, gamma is usually also emitted. So it usually accompanies the two. Alpha or beta. So because there's a lot going on in the nucleus, if an alpha particle is emitted, then the particles inside, the other protons, the other neutrons, they would have to reshuffle and reorganize themselves. So then gamma is emitted as a result of this reshuffling and reorganizing. Different radioactive decays have different properties. So some of the properties that we want to talk about is the penetrative power. We also want to talk about the ionizing power. And these are a little bit different. So if you guys can use the chat for a little bit and tell me, we have mentioned this before, tell me, what do you think the penetrative power is? And what do you think the ionizing power is? So if any of you can remember, put it into the chat for me to see if that sounds familiar to any of you. All right, some of you are getting good ideas. Yes, amazing. So a lot of you have answered that the penetrative power is the ability to go through different materials or to pass through things. So penetrative power is all about if I put paper or aluminium or lead or any other material like human skin, if I put that in the way of this radiation, is that radiation going to be stopped, or is it going to go through that? On the other hand, ionizing power, let's see what you have guys said. Ionizing power is the power that these particles have to ionize the air around them. That's a good way to put it. All right, so penetrative power we have said is how far it can go before being stopped. So alpha particle, we said this was the helium nucleus, so it's 2 protons and 2 neutrons, so that's pretty big, right? We have this big of a particle, so when you put paper between this, paper can actually stop it, so it cannot get too far. Beta, on the other hand, so beta is just an electron, so beta can go through the paper, but if you put in a fairly thick aluminium sheet, you can actually stop beta also. So some very, very thin aluminium sheets, it can still go through, but if the aluminum is thicker, it can be stopped. And then gamma, that one can get the farthest, and that's because it's just a wave. So if you put in paper, can get through it. If you put in aluminium, it can get through it also. It can be stopped by lead or concrete, we usually say, and that has to be fairly thick. So you can see we're saying a couple centimeters of lead or so much as a meter of concrete. So that's actually quite a lot. All right, so penetrative power, as we said, is how far or through what materials the radiation can go or before being stopped. All right, so alpha has very low penetrative power because it can be stopped by even something as small as paper. Beta would have kind of like a medium penetrative power because it can go through paper, but otherwise it's stopped. Gamma has a very high penetrative power because it can get through a lot of things. It has to be stopped by lead or concrete, something that is very heavy and dense. All right, so that's the penetrative power. And let's talk about the range. So a range is a third property that we would be interested in. So the range is, if I don't put anything in between the radiation and something else, how long does it travel before it decays spontaneously? So this is how far the radiation travels on its own. So gamma radiation is not a particle, it's a wave. It can travel for for quite a long distance. We're saying at least 80 centimeters. It can actually get a couple meters even, no problem there. So when we have a wave, you can think about light or about sound as wave also. So these get very far. On the other hand, alpha and beta are particles, so they cannot get too far on their own. Alpha can only get around 3 to 5 centimeters on its own. Beta radiation is a little bit lighter, so it's easier for it to fly, you can even imagine. So this would be like a middle range. It can get a couple times further than the beta. All right, so far, these are actually the same as the penetrative power or the order of it. We had short range and low penetrative power. For beta, we had a middle range. It also had kind of like a medium penetrative power. And then gamma, we said, is a wave, so it can get very, very far. So the range is very long, and we also have very high penetrative power. So remember, penetrative power is through how many materials can it get before it's stopped. All right, now the ionizing power that we talked about, it's something a little bit different, and many of you have said it very nicely. So ionizing power is the power of this radiation to practically cause damage. So we know that an ion is an atom that lost or gained an electron, right? That's what we said in the beginning. So when we look at ionization, we see this ion in it. So ionization means that an atom can strip or can get rid of its electrons, causing it to be ionized or charged. So when we've got this radiation coming in, if it has a high ionizing power, it means that if my radiation comes in, it can cause this other atom to get rid of electrons. Now, why is this dangerous? Because if we have something that is ionized, and remember, everything around us is made up of particles, of atoms, of molecules. If they are ionized, that means we said ions are very, very reactive. So a lot of things inside us can become ionized if we inhale or ingest, or if somehow the radiation gets to us. It means that the different particles of our skin, of our organs, or even such important things like DNA, even these things can in a way become ionized and reactive, and that can cause their damage. All right, so ionizing power basically tells us how harmful it can be for us to come into contact with this radiation. Okay, and this is very easy to remember because it's exactly the opposite of our penetrative power. So alpha particle has the greatest ionizing power. So alpha has the highest ionizing power. Beta, as usual, is somewhere in the middle. And then gamma has the lowest ionizing power. All right, so alpha and beta can cause much more damage to our bodies than gamma, although gamma can get the furthest. Okay. So, although of course radiation can be very dangerous, there are actually some practical uses for it. So some of the uses we have seen, or you guys might know about, is cancer treatment. So although radiation can cause cancer, it can also be used to treat cancer. So this is what you might come across a lot. We also have smoke detection as one of the uses. And that's because in a smoke detector, actually, so we'll look something like this, and we'll have this in one of our problems. So there would be like an opening down here. And as we have the radioactive radiation going in inside, if we have smoke particles, if smoke comes in to the smoke detector, it fills that space. So the alpha, alpha can be stopped even by paper. So if we imagine alpha particles going from here to here, right? So if the alpha particles go from there to there, we suddenly have the smoke particles coming in. They're going to go into the way of our alpha particles, and they're going to stop them. So the smoke particles stop our alpha, and so alpha cannot get to the other side. And because we've got good technology and all, this circuit, this smoke detector, will realize I'm not getting any of my alpha particles that I usually get. So something must have gotten inside, and that something was smoke. So that's going to set off an alarm. You're going to know there's smoke in the room. And so that's a very practical use. And some of the other ones that are definitely important would be pacemaker batteries, and something that you'll come across in the problems also are tracers for medical imaging. So in that case, I can't really draw a person properly, but if we need a tracer, the person will usually ingest a little particle that is radioactive, and as it travels through their body, as it goes to their stomach and all, or it can also be injected into their blood, so it can travel through wherever. As we look at the person through special things, we'll see where exactly that tracer is. So that tracer is going to be radioactive, and it enables us to see where exactly in the patient's body it currently is. So that's actually really interesting also. And another one that I wanted to mention is food preservation, because we'll see some food actually gets radiation onto it, and that's because it helps to kill some bacteria that we don't want there. And it can also be used to kind of stop, for example, fruit from ripening too soon. So when, for example, bananas or any other fruit is transported, so it can be also exposed to radiation so that it wouldn't get ripe too soon, and it can be sold to us normally in the stores. Okay. So the three things that we covered now so far were the radioactive decay. We talked about how it goes about. So we said that the atoms, or better said, nuclei, can become unstable and that usually happens because the ratio of protons to neutrons is not the ratio that we need. So there's either too many protons or there's too many neutrons, and then the nucleus becomes unstable. And our nucleus then tries to get stable, and it does that by emitting some radioactive particles or just radiation. So it tries to get rid of protons or neutrons. All right, so this is a process that we are familiar with, that we know. And then this radioactive decay, we've got three different types of that. And I'm hoping you guys remember by now. So we've got the alpha, we've got the beta, and we've got the gamma. Okay, these are the Greek letters for it. If you have this in an exam, it will either be denoted by these signs, or it will have the proper letters in it, like saying alpha like this. Okay, so that's all we talked about when it comes to radioactive decay. Stability is all about this ratio of protons and neutrons. So we talked about that also. And we talked about different ranges and powers of nuclear radiation. We had 3 different properties. The first one was the penetrative power. Then the second one was the range in air. And then the third one was our ionizing power. So I'm going to just do one thing now. And I'm going to put in an announcement. So I'm going to say that the penetrative power is the highest for alpha, beta, or gamma radiation. So you guys have that in the chat now. So vote on the option that you think is right. Which one of these has the highest penetrative power? And then I'm also going to do another thing for ionizing power. So is the ionizing power the greatest for alpha, beta, or gamma? So you guys have 2 kind of polls in the chat that you can look at. I'm just going to give it a little bit to see what you guys think. Also, someone asking if gamma is an upside down Y. So there is a couple ways to write gamma. This is just the way my handwriting is. You can see it as this, this probably maybe also. So that depends. All right, let's see what you think. So for the first question, most of you, the very big majority, said that the penetrative power is the highest for gamma, which is absolutely right. So let me get a yellow. So this is the highest for our gamma. That's true because we said gamma has to be stopped by either lead or concrete. And for the ionizing power, many of you are saying it's the highest for alpha, which is again true. So good job, everyone. And that's because alpha is a big particle, so it can cause a lot of damage to our bodies. Yes. All right, also got a great question here. How can beta emit an electron if there's a separate shell for an electron? So very good question. And this is because there is actually a whole process behind this going on inside the nucleus. So for beta, we know, so we've got a nucleus, let's say we've got, say this is a neutron, we've got another proton, neutron, and let's say we've got just way too many neutrons here. So we want to make our nucleus more stable. So we want to get rid of some neutrons. And this process actually, when I simplify it, to be honest, I'm simplifying here a little bit. So it does that by changing the neutron into an electron and proton. All right, so this is kind of what happens. We were talking about beta here. So neutron changes into electron and proton. So as a result of that, we have one less neutron and one more proton. But as you guys pointed out, that's absolutely true. An electron has no way of being in a nucleus, so the electron is emitted. So this is how it happens, fairly simplified. So before we had 2 protons, so now we have 1, 2, 3 protons, and we had 1, 2, 3, 4, 5, 6 neutrons. So we have 1 less neutron, 5, and we have an extra electron exiting our original nucleus. All right, so this is how that happens. So what I've got for you now is a little quiz. So I'm just going to copy in the link to our quiz. So you guys have that in the chat now, and I'll give you just a little of time to do it. It's just a little multiple choice, and you've got a couple of questions. We're going to go through the answers together in a little bit. Okay, just giving it 1 more minute. I know it's a short quiz, so we're going to go through that in a little bit. Some of you are saying, I'm going to address this as we go through the answers. All right, a lot of you are asking about the right answer to question 5. If you guys refresh the quiz, I just checked, it should be okay. So I just checked that for you. It should be okay now, definitely. You're going to go through that in a little bit. All right, got many answers, which is awesome. So let's look at that together. So question number 1, and just seeing that so many of you got this right, that's so amazing. All right, question number 1 is, which of these is equivalent to emitting electromagnetic radiation? So we know electromagnetic radiation kind of like we would say this is a wave, right? And out of the 3 different decays, 3 types of radiation that we talked about, this will be the gamma. So we know gamma is just a wave, and it's very high energy wave. All right, question number 2. We've got which of these 3 is equivalent to emitting a helium nucleus? So we mentioned that the helium nucleus, is what's inside the nucleus of an element called helium. And these are 2 protons and 2 neutrons. So that's what's inside a helium nucleus. And we know a helium nucleus, or 2 protons and 2 neutrons, is an alpha particle. Or we can write alpha as this Greek letter. So that's question number 2. And then question number 3 told us which of these 3 is emitting an electron. So obviously this is going to be the 3rd one that we didn't mention, but we know an electron is a beta particle. So it's the beta, or we can write beta also as this. Okay. And for the 4th question, we're asking which of them has the highest ionizing power. So that's the one that I just quiz you on with the chat poll. So the highest ionizing power is the alpha. And then on the other hand, the highest penetrating power, which is question number 5, that's going to be gamma, because we said we need like concrete or anything like that to actually stop gamma from going further. So I just checked that for you, and it says gamma is the right answer here for me. So sorry if it didn't. For some of you guys, maybe try to refresh the page. But yeah, so gamma has the highest penetrative power. Now what we're going to do is go through just a couple questions that were in past papers, so you would get a feel of what these questions could look like. So here, without even the intro on that, the first question was an alpha particle, and this was pretty much in the quiz just now. So we know an alpha particle is a helium nucleus. Another way we can also write this is that it's 2 protons and 2 neutrons. And if some of you guys are familiar with this notation that we'll go over in a little bit, we can also say it's the helium nucleus like this. So this is the equivalent of saying helium nucleus. All right, so any of these 3 is absolutely fine. Now, from which part of the radon atom does the alpha particle come? If we just look at what the alpha particle actually is, so it's a helium nucleus, and we know all the radiation that goes on comes from the nuclei, right? We said that radioactive decay is all about unstable nuclei. So if it's the nucleus that's not stable, of course, the particle has to come from the nucleus because that's what we want to change. Okay. Now, another one that we've got here is that we've got a radioactive source here on the left, and we've got 3 different paths of probably alpha, gamma, and beta radiation, but they're called P, Q, and R, so we don't know which one's which. Something that we can use as a hint, though, is that we've got a negatively charged plate here and a positively charged plate here. So what we can read from that is that Q is not attracted to either. We also know that P is a little bit bent towards the negative plate. And if it's a little bit bent towards the negative plate, we can say it's attracted to the negative, which means that it in itself has to be positive. All right, so we would know that negatives are attracted to positives and they would be repelled from the same charge. Okay, if it's opposite charge, they're attracted. All right, so the R is exactly the opposite. R is attracted to the positive plate. That means that R itself has to be negative. Okay, so now that we know this, we just have to figure out which of our beta, alpha, and gamma radiations are positive, neutral, or negative. So an alpha particle, we know, comes from the nucleus. And we know from our previous lessons that a nucleus is positively charged. And that's because there are protons inside. So nucleus or alpha is going to be positive. We've got beta as an electron. And you should know that electrons are all negatively charged. And then gamma is just a wave. So this gamma is not going to have any charge. So we can say no charge at all. Now let's just match these. So you're asking which of them is alpha. So we know alpha is positive, and we also said that P is positive, so alpha has to be P. And then for gamma, we said gamma doesn't have any charge. That means it's not going to be attracted to either the positive or the negative plate. So that's going to give us Q. All right. So that's that. And this one comes to the penetrative power that we talked about. So we want to keep each radiation source inside a different box. So we can only use one for each. And we want the least amount of radiation coming in, get into air. So we've got aluminium here, cardboard, and lead. So what should we keep where? Give you a little bit to think about that. And so what we should think back to is that alpha can be stopped by paper, right? It doesn't have too much of a penetrative power. So if we put that into the cardboard and it tries to escape, it's going to be stopped by this cardboard. If we put in gamma, that would escape, no problem. So if you're going to put alpha in there, we know beta can be stopped by, well, fairly thick aluminium. So we can place beta into this, because if it was in this cardboard, it would actually go out, which is not what we want. But if we put it into our aluminium, it will go there, maybe penetrate it a little bit, but it wouldn't get out at all, which is what we want. So that leaves us with gamma, which we need lead or concrete to stop it, and it leaves us with the lead box. And we can see the lead is very, very thick, so we actually need quite a lot of it to stop the gamma radiation, because it might get like halfway through, but it wouldn't get out. Okay. Now here's a little math problem. So we know, reading through this question, that even 100, sorry, let me just find my pen. Even 100 millisieverts, that would be like the lowest dose that anyone could be worried about, that could be dangerous potentially to their body. Now, we've got this 0.003 millisieverts per day if you're in a granite rooftop. So is this going to be dangerous to us if you're there over a year, or is it not? So we've got a dose of 0.003 per day. So if we want to calculate how much that is per whole year, we have to multiply that by 365 days. All right, so this is per day, and this is days in a year. And if you guys put that into your calculator, I'm sure some of you are putting the answer in, which is great. I love you seeing engaging, so feel free to put in the answers you think are right as I go along. But this gives us just over 1 millisievert, so it's 1.095. So when I compare that to the lowest dose that I should be worried about, that's like 100th of it. It's like 1%. So I don't have to be worried about this dose because it's much smaller. It's much smaller than the 100 millisievert that could potentially cause any damage to me. All right. Now, I talked about sieverts, and I've mentioned that this is one of the units that we can use to talk about radiation. And this one I thought was fun because bananas, although many of us don't know it, are a source of some background radiation, and it was suggested to use banana equivalent dose as a unit. So apart from the reason that it just sounds fun, right? What could be some reasons that this unit could actually make the public more aware of radiation risks? So if you have any ideas, drop them into the chat. I'm going to go through them. So other than that, it sounds fun. What are some practical reasons why we could use banana equivalent as unit instead of sieverts? All right. Yeah, so many of you guys are saying this. It's easier for everyone to relate to. Everyone knows what bananas are. It's easier to remember also, definitely. Who remembers seabirds? So yeah, all of these things that you guys said are absolutely right. So it's more relatable. Everyone knows what a banana is. Not everyone knows what a seabird is. So we can compare the risk dose. So we can compare the radiation risk or potential damage or hazard much easily to this equivalent of bananas or this risk or radiation dose from eating bananas much more easily. All right, so if you are ever in the position of being able to change these units, we definitely have some reasons for us to do so. Okay, on to a different topic. This is a diagram of a smoke detector. So it's kind of what I talked about before when we talked about different uses. So we've got a alpha radiation source, and this radiation is going to this other plate. And what happens when we get these smoke particles? Grab in a different color, let's do red because it's dangerous. So we've got these different smoke particles, and if they get here, you can see it stops the alpha from reaching the radiation detector, because alpha can be stopped even by something as small as a paper or as thin as paper, so the small particles are enough to stop it. So anything along these lines, I actually gave that away right away. But anything along these lines would be a good answer to this question, because the smoke particles that we see entering our detector, these would absorb or stop our alpha radiation it would stop it from reaching this detector. So if no alpha radiation goes to the detector can know, oh, the alpha particles are coming in, there must be smoke. I have to set off the alarm. Now, we saw that alpha particles can be stopped by smoke. And there is a good reason why we use alpha particles and not beta or gamma. Now, thinking back to penetrative power, what do you think would be some of the reasons that beta or gamma would not be a good source of radiation to use for smoke alarms? So we know smoke particles stop alpha. So why can't we just use beta or gamma for this same cause? So why would beta or gamma not help us detect any smoke for a smoke detector? Again, just drop a couple ideas into the chat. Yes, absolutely. You're so right. So I think everyone who dropped an answer there, absolutely right. So we know beta and gamma have higher penetrative power. So both would not be affected. So they would get through the smoke, which means when I go back to the previous slide, if this was beta, it would go right through these smoke particles. Same for gamma. So there wouldn't be any difference. So there wouldn't be, let me grab a pen. No difference in, let's say, in the count rate on the detector. All right, so many of you have put that in, which is amazing. So that will be the main reason. Okay, so we talked about radiation. Now we're going to go ahead and dive into nuclear equations, which is something fairly new. So just make sure you pay attention here. And the first two things I want to emphasize are what are alpha particles, what are beta particles. We mentioned this many times, but so this is alpha, right? Alpha is 2 protons and 2 neutrons. It has a positive charge. We also have beta, which is an electron, and that is negatively charged. Okay, now coming on to gamma. Gamma, since it's just a wave, we're not going to talk about it here in the nuclear equations. But this is what we need to get comfortable with. We'll have an element. So this is going to be a letter or 2 letters. So that's an element. And then we'll have mass and atomic number. We went through these before, so I'm just going to be a little bit quicker. But a mass number is the number of protons plus neutrons, whereas the atomic number is just the number of protons. So if I have a particle or an element that has 1, 2, 3 protons inside and 2 neutrons, so that's 3 protons, 2 neutrons. Right, so I'm just going to follow the guideline that's set over here. The atomic number we say is the number of protons, right? So atomic number is the number of protons, so that's 1, 2, 3. The mass number, on the other hand, the mass number is protons and neutrons, so it's both. So we've got 3 protons and 2 neutrons, so altogether that gives us a 5. All right, and what you need to remember is that the top number is the mass number, so that's always going to be higher. And the bottom number is the atomic number, so that's the lower number. All right, so we could write our element here as 5, 3, and some element. Okay, so these are the mass numbers and the atomic numbers. And when we think about our alpha particle, we know alpha particle is a 2 protons and 2 neutrons. Right, so this bottom number, that's number of protons, so that's just a T, whereas the top number is number of both protons and neutrons, so that's a 4, right? T plus T, that's just giving us a 4. Now with a beta particle, it can be slightly confusing because we suddenly have this -1 here. And we'll have the mass number, the top number. We know beta is just an electron. So we have 1 electron. which is neither a proton and neither a neutron, so we give that a 0. Now what's interesting, and we put this -1 here for the electron, and the way to remember this is just because an electron is, we can think of it in a little bit as the opposite of a proton. So because it's the opposite of a proton, instead of a +1, we write a -1 here. Okay, it's electron changes, and so we put in a -1. These two are really, really important to remember. Okay, write them down somewhere on a paper until you remember what they are. So alpha particle, 2 protons, 2 neutrons, and this He stands for helium. We said it's a helium nucleus. Whereas beta, there are no protons and no electrons, no neutrons, so that's a 0, and it's a -1 here, down here. And the E stands for electron. All right, so 2 things to remember. So the question that you might come across can look something like this. What if a uranium atom has a mass number of 238, an atomic number of 92, and it experiences an alpha decay? So this is what it would look like. This is uranium, and the mass number is on top, and the bottom number is the atomic number. So that's 92. Okay, so it experiences alpha decay. That's why we have this alpha here. And we know alpha has a mass number of 4 and an atomic number of 2. So this is kind of like an equation, which means all the numbers on the left have to be equal to all the numbers on the right. So here, what we have is 238 being 234 plus 4. That checks out, right? What about on the bottom? We've got 92 is equal to 90 plus 2. And this is how we would do these. All right, if we've got, and let's say 232, I'm just making up numbers here, and I'm going to call that E1 for an element, and that changes into something and an alpha particle. Now, how do we solve this? We know an alpha particle has a mass number of 4, atomic number of 2. How do we fill in the numbers here on element 2 though? Well, we've got 232 is equal to something plus 4. So the something has to be 228 for it to make sense. What about the bottom? We've got 86 is equal to something plus 2. So 86 is going to be 84 plus 2. And this is how you would do that. You don't need to know what elements they turn into. You wouldn't have to remember these names or these abbreviations at all. You would be told these, so you don't have to know that. All right, so that's on alpha. What happens when a carbon atom has these atomic and mass numbers, experiences a beta decay? So this is what the equation would look like. Again, we know for beta, we had mass number of 0, atomic number of -1. That's something we should remember. Now let's check our equation. So we got 14 is equal to 14 plus 0. That's all good. what about 6 equals 7 minus 1? That's also good. So this equation is absolutely right. Now let's try, for example, back to the uranium. So we had T3890T uranium, and it changes into something. We don't know what it is. I'm just going to call it an element, plus beta. Now, how do we find the numbers for our element? First step is we know a beta has a mass number of 0, atomic number of -1. And now we just finish our equations again. So T38 is equal to something plus 0. So this is going to stay the same. On the bottom, we've got 90T equals something minus 1. So that has to be 93. 93 minus 1 is 90T. So that would be that. So let's try this. An element of T20T and 86 goes into something alpha. I'll give you guys just a couple seconds to think about it. What do you think would be the mass and the atomic numbers of the new element that is going to be right here? So just giving you a little bit to think. Love that. Already getting some answers, which is amazing. Okay, here's the answer. We would have T18 and 84. Why is that? Because for an alpha particle, we know we've got a 4 and a T. So T20T is equal to T18 plus 4, and 86 is equal to 84 plus T. So that all checks out. So good job everyone who tried it. If you guys didn't get it right the first time, you'll get it right the second time. So what we did in this little mini chapter was talking about nuclear equations, right? We now know nuclear equations are these that we just saw. This is a nuclear equation. And we learned how to balance them. This means complete the missing numbers. Right, that was finding out the mass numbers and finding the atomic numbers. So what I've got for you now, so everyone can have a go at that, is again a little quiz. So I'm going to copy in the link, and I encourage all of you to just have a go at that, whether you're sure about it or not yet. So have a go at it, and I'm going to write down a little hint here. And that's that alpha has a 4 and T, and beta has a 0 and -1. All right, so what I encourage you to do is write down equations. Actually, write it down on a paper, and you'll see what you get. So I'll give you guys a little bit more time on this one because it's a little bit longer and it's not multiple choice, and then we'll go through it together. Also, some of you are asking about gamma. So gamma, since it's just a wave, it wouldn't appear in the equations, and even if it did, it would have a 0. So if you ever come across gamma there, let me get a pen here. Whoops. So if we had gamma there, it would have 2 zeros for anyone interested. I know a couple of you are asking, but it usually wouldn't come up anyway, so nothing would change there. Okay, got a good number of answers in. So by the way, I leave all my quizzes open even after a lesson. So if you want to bookmark the page and come back to it, try it again, you can always do that. They remain public and open. I don't ever do anything to them. Okay, someone's asking, how can you tell the mass and the atomic number apart? So if you get it in a problem, you would be told something like the mass number is, or the atomic number is, but that's going to be too late. The upper number is always the mass number, and the lower number is always the atomic number. Also, if you have two numbers like this, the one that's higher, like 4 is bigger than T, then the 4 is the mass number. The mass number is always going to be bigger than the atomic number for normal particles like this. You can definitely favorite those quizzes in your Chrome tab. That's absolutely fine. As I said, these are for you to practice. So if you want to come back to any of the quizzes that I made throughout the year, you can absolutely come back to them. They're all working and active. Okay, I got many answers, and so many of you are getting that right, which is nice. So we're going to go through the answers together now. So looking at the first and second question actually together, we've got an element with mass number 90 and atomic number 36. So I can write that as 90, 36, and an element. I'm going to put in an E. And this undergoes a beta decay. So I'm going to write down a beta. And we have another element, I'm going to call it ET. So first things first, I need to remember what beta is. So beta has a 0 on top and -1 on the bottom. And now I know that 90 is equal to 0 plus 90. Okay, so that's on the top. And on the bottom, we've got 36 is equal to -1 plus 37, right? So these are just balancing equations. 37 minus 1 is 36. Now, which of these numbers is which? As I said, the top number is always going to be the mass number. So that's the answer to question number 1, I believe. So the mass number is 90 and then the number on the bottom, that's always the atomic number. So here, the atomic number is 37, and I believe that was question number 2. Yes. All right, so the reason I'm telling you guys to write it down is because it's so easy, for example, here to write down 35 instead. But when you write it down as I just did with the equal signs and the pluses, you can very easily check that 36 is -1 plus 37. If you had a 35 there, that equation wouldn't make sense to you. So that's a very easy and quick way to do this. So don't try to do it in your head, because it's so much easier to get it mixed up. All right, let's look at the second pair of questions. So that's questions number 3 and 4. So we've got the same elements, so 19 and 36, but this time it undergoes an alpha decay. So we've got an alpha, and we've got some other element that we can call ET, E3, or whatever you want. So we're going through the same exact process. We know alpha has mass number of 4 and an atomic number of 2. So now again, it's just balancing these equations. We know 90, always put the equal sign over that arrow. 90 is equal to 4 plus 86, and 36 is equal to 2 plus 34. Okay, you can actually put in that equal sign in pencil, that's fine. So 90 is 4 plus 86, 36 is 2 plus 34. Now, which one is which? Again, the top number is the mass number, and the lower number is the atomic number. So let's see which question asks for what. Another thing to do is read the question carefully. So I've got a couple 86s here for the 34. Question number 3 says which the atomic number. So that's asking for this 34 here. That's question number 3. And question number 4 is asking about the mass number. So that's the number over here. And I have majority of you put in the 86. A couple of you put in the 94. So you guys just try to write it down. And I think that's a really good hack on how to always get these right. All right, you're a little bit towards the end of this chapter. You're just going to go through some past paper problems together. But before we do that, I want to let it sit with you for a little bit. So we're just going to have a quick early break. So it's 11:24. So we're just going to be back at 11:29. So have a good little break. And be back in 5 to go through some past paper problems. All right, see you in a bit. Okay, welcome back. I hope you had a good break, got a break from the computer screen, maybe had some water to drink or something to eat, a little snack. So we're going to go through some past paper problems on this and then get into a new topic. So the first question that we've got is kind of similar to what we had with the questions I just went through with you. So we know we are actually told the mass and the atomic number for our helium or alpha particle. So we know this is the same as saying 40 with an alpha. They're the same thing. And we now have an equation, a nuclear equation here, and we're supposed to find the numbers. So this is exactly the same that was in the quiz. Don't let it scare you with all the talking around. Just getting straight to that equation. So if you are looking at this and you think you know the answer, drop it into the chat now. I'm going to go through that with you, but if you know how to do it, feel free to do it. And what we're going to do is the same as before. So we've got 212 here, 212, and that has to be equal to the numbers, to the mass numbers that are here on the right. So on the right, we've got 4, and we've got a missing number. So 212 is equal to 208 plus 4, and that's it. So that's a 208 on the top. And on the bottom, we've got an 83 being equal to something plus 2. So just thinking about algebra, we've got 83 is equal to 81 plus 2. All right, so any questions that you would get similar to this would look quite like that. The only difference might be that you might be asked to find these numbers on the left. But the process is quite the same. All right. Here we're looking at the same kind of process, but the question is about something else. So we've got 2 different decays. We've got alpha decay and we've got beta decay of the same element. And we're asking why the resultant element, so that's what we get from the decay, why cannot it be the same? Now, this is quite a tricky question, and we are going to come back to something that we talked about last time. And that's about what actually tells us if the elements are the same. So an element, if we've got atoms that have the same atomic number, so that's the bottom one, then these atoms are then of the same element. Oops. Let me write that again. So we've got then the same element. There we go. All right, so it's the atomic number, or we can say number of protons that determine whether that atom is of the same element or not. This is something that I covered last month, so I'm not going to go into great depth about it. If you're not sure, go ahead and ask a question in the forum. I can get back to you, or the moderators, or you can just watch the recording from last time. So it's the atomic number that tells us whether the atoms are of the same element. Now let's look at alpha and beta decays. Alpha is a 4T particle, whereas beta is 0 minus 1 particle. So looking strictly at the atomic numbers, we've got a 2 and we've got a 1. So these two lead to different changes in the atomic number. So the resultant element cannot be the same for both. All right. So alpha and beta leads to different changes in the atomic number. And that means that the resultant atom or element, so we can say the new atoms will have different atomic numbers, and that means that it's not going to be the same element. Okay, so that's quite a long answer to it. You can use number of protons instead of the word atomic number. That's absolutely fine also. All right, and one more question here is that looking at this right here, this curve, this was predicted. This was how the decay was predicted. So this tells us how many counts per minute there were. So these are these green dots. So these green dots is how it actually was in reality. All right, so that's what we got from measuring it. So green dots is how many counts per minute there were. There is a way, and we'll talk about that in a little bit, there's a way to predict when the decay will happen. And this prediction can be put into graph, and that's in the red curve. So this is prediction. And we can see that the prediction doesn't match the reality. And my question, or their question also, is why is that so? What can we tell about the radioactive decay? What kind of process is it? So I'm just going to give you a couple seconds to think about that. Why don't the actual data match our prediction? It goes to one word actually that I mentioned before that I said was important. So many of, yes. Okay, thank you for everyone chipping in. Perfect. So I'm going to give it away also. And the answer is that it's a random process. So although we can try and predict anything about it, we can kind of fairly well, you can see that on the graph, we can fairly well guess when it will happen. It's still random. So there is nothing in the world that can tell us when exactly it will happen. It's literally random. So good thing to remember, it might come up. Okay. So much about the nuclear equations and anything that's connected to it. What I want to talk about now are so-called half-lives, or when we just use the singular half-life. So before I dive into it, I want you to again use the chat and tell me, have you heard the phrase half-life before? Do you remember it from last month? Do you remember what it means? Or just give me like 1 or 2 keywords about half-life, anything that comes to your mind when you hear it. So I'm going to give you a little bit of time to do that. Okay, I'm getting some really good answers. So some of the ways to see this is the time it takes for half of the particles to decay, absolutely. How long it takes for the atom to decay, to the amount of neutrons. Time taken for half of the nuclei to decay. Yeah, so most of you are putting in the keywords that I was looking for. Exactly. Time by which half of the decay will happen. So we know this is a random process. So half-life is, as we said, time it takes for the number of nuclei in the sample to halve. Or, as we can say, time taken for half of the unstable nuclei to decay. All right, most of you have said that. That's so amazing. So we've got, let's say we've got 100 nuclei that are unstable. Then when one half-life happens, you're going to get 50 nuclei. When another half-life happens, so that's 2 half-lives together, we're going to get again half of that, so that's 25. And we could go on and on and on. So this is our tool to kind of predict radioactivity. We have observed different elements, and we have seen how fast or how slow they decay. And based on that, we invented this half-life to tell us approximately, that's a very important word here, approximately when will half of the unstable nuclei decay. So as we saw before on that curve, we cannot predict it exactly, but we can use our half-life to say approximately in half-life 50 of these nuclei will be gone. So another thing to mention here, let me take this away so you can see it also. Another thing that you see over here are different so-called isotopes. So this is just something for you to kind of recall from last time. We've got isotopes of atoms. So isotopes are the same element. Let me use a different color. Isotopes are the same elements. So they've got same mass number, but they've got a different number of neutrons. Right, so this is just something for you to recall. It's not strictly related to half-life, it's just something for you to recall. Okay, so as we mentioned, this process of decaying is very much random, and different isotopes and even different elements also have different lifetimes, half-lives. So we've got 3 examples here. So we've got a carbon-14 that has a very, very long half-life. Now, when we look at plutonium, though, let's look at that half-life. We've got 24,000 years. So plutonium has a very, very long half-life compared to, for example, phosphorus. So that only has around 14 days of a half-life. That's around 2 weeks. What does that mean? If I have 100 nuclei of plutonium and of a phosphorus, and I leave them for 2 weeks, I'll leave them for 2 weeks. That means I'm most likely still going to have 100 nuclei of plutonium because nothing's really going to happen to it. They have 24,000 years to decay. Whereas in phosphorus, the 2 weeks are about a half-life. So in a half-life, half of the nuclei are going to decay, so I'm going to be left with approximately 50. All right, so there's a very big difference, and there's also a different use for these different elements. What we'll see a lot, and what we'll actually also draw, is a graph of half-lives using the time and how many isotopes or how many nuclei are still left. So this can be a percentage on this axis. It can also be number of nuclei left, for example. And so what we know that if we start off, time is equal to 0, we started with 100%, we start with all the nuclei, right? And then we get to 1 half-life. We said 1 half-life, half of the nuclei are gone, so we get a 50%, because half are gone. Now another half-life, we've got half of the 50% gone, so that's 25. When we go on to 3, we've got 12.5%. Right, as we go into 4, we get like 6.25% left. So you might notice it approaches 0, but it never quite gets there. So one of the things that we can talk about here is either the count rate or the number of nuclei that are left. So if we've got an isotope or an element that has a half-life of 2 days. So let's see what happens. Count rate, we said, is the number of decays per, we've got second here, so we'll keep the second. So this can be related to number of unstable nuclei left. So we're starting at time 0, which means no half-lives have happened yet. So we've got 40,000 as our count rate. Now after 2 days, 2 days is 1 half-life, as we're told. So that's 1 half-life. So that goes down by a half. We're now on 20. As we go on, it's exactly the same process. 3 more days, we've got 2 half-lives altogether. And a half of 20,000 is 10,000. As we go on, you could go to 6, to 8, to 10. You could go on forever, pretty much. So for example, after 10 days, we've got 5 half-lives. So it went down 5 times once, twice, 3 times, 4 times, and 5 times reduced by a half. So the count rate is half every single time after half-life happens. The word half comes across very many times here, so that's a good way to remember it. So one of the ways to calculate the net decline, so the net decline is the total decline or how much we lost. So one of the different ways to calculate this is find, for example, if you're looking for the count rate after 3 half-lives, so that's after 6 days. If I want to know what's the net decline, I'm going to find the count rate, that's 5. And I'm going to find the original count rate, that's 40,000. Both are in thousands. So I'm going to find these two, and I'm going to divide them. So 5,000 divided by 40,000 is 0.125. Another way that we can do that is we know that with each half-life, this decays by a half. So we can say that after 1 half-life, it decays by a half, after 2 by another 1, after 3 by another 1, and you get the same result. So it's up to you whether you want to do it through the count rate, and you can just divide them, and you get 1/8, or you can multiply the halves so many times that you get the amount you want. If you're looking for 5, we can say it's 1/2 times 2 times 3, or 5 times in a row, or we can divide this by the original count rate. So these are 2 methods that are equivalent. They're exactly as good as the other. So let's see. What do you guys think is a decline after 4 half-lives? So how many percent we can say, or how many nuclei are still left? Are left, or what's the count rate compared to the original? So if you have any ideas, drop them into the chat. You can drop the result. I'm going to go through it with you both ways. So we know one of the methods is to find this is probably too light of a color. Let me pick purple. We can find the corresponding count rate. So we've got 4 half-lives, so that's this right here, 3750, and divided by the original one. And the original one is 60,000. And when we do that, we get 0.0625. Or the other method is to say, well, after one half-life, we've got a half. After another one, we have to multiply it again. Third one, fourth one. So when we multiply this out, we get 1/16, which is the same as 0.0625. So both of these, you get the same result, and this is what's the net decline, or how many nuclei are left. So we can say this corresponds to 6.25%, right? So there are still 6.25% nuclei left. Okay. So just going to see, oh, good. All right, just look at the answers that you guys put in, which is amazing. So many answered either in the decimal number or in the percentage. Both are equally okay. All right, so we talked about half-life and we talked about net decline. So remember, in half-life, that's the time it takes for 1/2. That's where the name comes from, for half of the unstable nuclei to decay. And we should put into consideration that this is not exact or very, very accurate, as the radioactive decay is a random process. Right, so this is used as an estimate. And something we can also remember is interesting fact that different elements or even different isotopes can have very, very different half-lives. And we saw that some elements can have a half-life as short as 14 days. And some elements can go on for thousands of years. So we could have over 20,000 years. And some elements or some special isotopes can have a half-life as short as, for example, 6 hours. So there's actually a very, very great variety between the different half-lives. And this is then going to kind of say what these elements or these isotopes are going to be good for. So these can be good for different uses. So something that you'll come across in your questions is, for example, if we've got something that has a half-life of only 6 hours, it can be used as a medical tracer. Now, why is that so? If it has a half-life of 6 hours, then it will actually decay and it will get to stable state after a very short time. And after it's stable, it's no longer, for example, harmful to the body, and we don't need it either. You wouldn't need a tracer for too much longer than that. So we can use something that has a half-life of 6 hours, for example, as a tracer. On the other hand, we might have something that has a half-life, for example, 2,000 years. Now, this can be used, for example, to approximate age of things. So you'll see this with carbon. I don't know from the top of my head what the half-life of carbon is, but we'll come across it. So for carbon 14, we have some carbon-14 in our bodies. We get it through food and mostly through food. So then when people die, they no longer get more carbon-14 from food. So no longer new carbon. That means carbon can decay. So by looking at how much carbon is left, so if it decays, there's less and less carbon over time. So seeing how much is left, we can relate how much is left to how much there was originally. Right, so we can look at these two numbers, and from that we can estimate how many half-lives happened. So if there's, for example, a quarter left, it would mean that 2 half-lives happened in between. And if we know the half-life is 2,000 years, then if 2 half-lives happened, we know that the skeleton, so if we've got 2 half-lives, for example, we would know that the skeleton can be just around 4,000 years old. So this is actually a method that is used in practice. Don't quote me on the 2,000 though, we'll see this in a problem specifically exactly how much it is, or you can look it up. Okay, so that was all about the half-life. And then we also talked about the net decline, which was all about how many or how much, let's say how many nuclei or unstable nuclei are still left. Okay, and we did this by knowing how many half-lives. So number of half-lives, that's how we know. So we can either do it through the count rate as I showed you, or we can say, well, it's 1/2 times 1/2 and so on, and you do this the number of half-lives you get. Or we can say that's 1/2 to the power of n, where n is the number of half-lives. Because we can see we're always multiplying the half by itself. So if you multiply a half by itself 3 times, it's the same as 1/2 to the power of 3. If you're not sure about that, just drop a question into the forum and we'll answer. So this is one of the ways to find the total decline. All right. One more quiz for you. This is actually the last quiz for today. So if you haven't participated in any quizzes yet, make sure you give this one a go, or you can just bookmark it and try it later on and come back to it. So I'm just going to go ahead and get our link. Okay, so this one should be the right link. So I encourage you to get a piece of paper and try the questions. If you're not sure about any of the questions, you can just skip them, and I'll give you some time and then go over it with you. Okay, going to give you some more time. I know this one takes a little while, so don't be restricted. So someone asking, are questions 1 and 2 the same? They're not. So make sure you read the question. And the first one, it asks how many nuclei are left after 2 years, whereas in the second one, it's 2 half-lives. So it's not the same thing. How that helps. Okay, still going to give a little bit more time. Also, I see some of you guys put in the word month in the last question. And it might have told you it's wrong, so try to put that. All right, I think it's time to go through it together. So as always, you can come back to the quiz, try it again, or try like whenever if you want to, or finish it later on. I'm just going to go through some of the questions with you now. So first question, we've got a half-life of 2 years. All right, and we originally have 4,000 nuclei, and we leave them for 2 years. So 2 years is 1 half-life. So the number of nuclei that will be left afterwards is 4,000 times 1 half. Only 1 half because we've only got 1 half-life. So you can do that with a calculator also. We get a 2,000 from this. So that was the right answer. let's see the second one. So we've got the same element. So again, we've got a half-life of 2 years. And we originally have 4,000 nuclei. Now, after 2 half-lives, this time, how many are left? So we've got after 2 half-lives, and that means we can say it's 4,000 times 1/2 and 1/2 again, or you can also write it as 4,000 times 1/2 squared. The square here is the number of half-lives. All right, that's why I put the t there. It's absolutely up to you which way you do it. Here it's fine also just putting it that. So what we get from that is 4,000 times 1/4. So we get 1,000 nuclei from the second question. Okay. So I put that there on purpose just for you to make sure to experience both. So sometimes you'll see amount of years or days, and sometimes you'll get the number of half-lives. So just make sure you read the question right and you answer what they're asking you. Okay, let's see the third one. So here we've got a half-life of just 7 days. And originally they were 6,000 nuclei. And after 2 weeks, how many are left? So again, I see a lot of answers that say 3,000, assuming I'm asking after 2 after 1 half-life probably. So just make sure you read the question right. So we have after 2 weeks. That's after 14 days, right? So after 14 days, that's 2 half-lives. If we've got 2 half-lives again, we can either put in times 1/2 and 1/2 again, or we can put in 6,000 times 1/2 squared. Again, absolutely up to you in this case. So when we do that, we get 6,000 times 1/4, and putting that in, you get 1,500 for your answer. Again, most of you got that right, which I think is great. All right, so question number 4, which I thought was a little bit more challenging maybe, but it's the same process pretty much, is we've got a half-life of 2 days in this case. And again, it's just really important to make sure that you do the same process, you realize what the units are you in. So originally we had 64,000, and now we're looking at it after 2 weeks. Oops, after 2 weeks. So since we were told the half-life in days and not weeks, we want to convert this into days, so that's 14 days. So we've got 1/2 half-life is 2 days. We've got 14 of them, so that's 7 half-lives altogether. So exactly the same process. Here we've got quite a number of half-lives, so if you still want to, you can of course write out 7 halves like this. That's a 5, 6, 7. But I would encourage you to maybe just use the exponent, and we can say that 64,000 times 1/2 to the power of 7. So these two are equivalent. It's just that when you put in 7 halves like that, it's very likely you'll make a mistake somewhere just because of like typos and stuff. But as you put that into your calculator or anywhere, you get 500 as an answer. So that's the right answer to that one. So yeah, just make sure you read days and weeks and you check your units. Okay. Last one was the most challenging, I would say, because it's the opposite process. We're told the beginning and the finite amount, and from that we're supposed to find the half-life. So let's look at that. We've got originally 2,000 nuclei, and now we've got, after a year, we've got 250. And so this is the beginning value, this is the finite value. So let's see how many half-lives we went through. So we had 2,000, and after one half-life, we get 1,000. After another half-life, we again have to divide that by 2. So after 2 half-lives, we've got 500. Okay, that's still not 250, so I'm going to try again. And after another half-life, we get 250. So that means we went through 3 half-lives. Okay, we're on a good way, and we know these 3 half-lives that happened after a year. So 3 half-lives is 1 year, or we can say that's 12 months. All right, so if 3 half-lives is 12 months, then 1 half-life is 12 divided by 3, so that's giving us 4 months. Okay, so this is the process you would go through. You have to find the number of half-lives that happened and then relate that to the number of months or days or weeks or whatever. I've had a couple of you say 4 months in the answer, so it probably said it wrong for you because you are supposed to just put it as a number. So if you put in 4 months, it was the right answer. You just put the months there. All right, so this is the quiz, and I've now got quite a number of different paste paper questions that we can go through, and we'll see how far we get before lunch, and then we'll just continue after lunch. All right, so starting with this question 3B, we've got a sample that contains 40,000 radon atoms. So we've got the initial value, and we've got the half-life, which is 4 days. And we're supposed to actually draw this graph over a period of 12 days. So there's a bunch of different things to do this. And so what we have to decide first, so this is the time, and we've got 12 days to fit in. So this is going to be our 0, and this right here is the number of radon atoms. So we've got 12 days to fit in. So first thing first, we need to decide on our axes. So I've got 1, 2, 3, 4, 5, 6 points here. So I'm just going to make it by 2 days, 10 and 12 to fit in the whole 12. That's the first thing. Then I need to fit in 40,000 radon atoms. Got 1, 2, 3, 4, 5, 6, 7, 8 different points. So I could make the step 5,000. So that's 10,000. That's 15,000. That's going to be 20,000. So just make sure that you fit in your limits. You have to fit in 40,000 there. So make sure you have your axes labeled. All right, now on to the actual points. So we know initially at time is 0, so that's 0 half-lives. We get 40,000 nuclei. All right. So that can actually be our first point. Okay. Now we know the half-life is 4 days. So after 4 days, that's 1 half-life. This is going to decay by a half. So we've got 20,000. Let's put that in. We've got 4 days, and we've got the 20,000 right here. I hope you can see the blue all right. All right, so another half-life happens after another 4 days. So that's 8 days total. And we've got 2 half-lives. And this is again going to become only half of it. So we get a 10,000. So 8 days, 10,000. Okay, that should be visible. And then when we go on, we've got 12 days. That's 3 half-lives. And again, this is going to become a half of it. So that's 5,000. And I'm going to put that over here for 12 and 5,000. So we've got our points, which is great. And we're now going to try to connect them. One thing to do is do not connect the dots by straight lines. All right, that's just a no-go. We will try to create a curve. Okay, so here, to be honest, bear with me because I'm on a computer, so it's kind of hard to actually go through the points. But we're going to try to, okay, there we go. So this should kind of resemble a curve. You don't want to go like point to point straight lines. You want it to be a little curved. You will, I think, get marked down if you just put in like point to point straight lines. So there we go. This is a way to draw a graph like this yourself. You can put in a little table next to it, so just to make it easier for you, but you don't have to. The important part is that you have your axes labeled. You've got points, and you've got a line. All right, so have your axes labeled, have points, have a line. Make sure that your endpoints are the ones that you were told to have. Okay, how that all makes sense to you? Let's see the other one. So I'm just going to flick back and reset. The half-life of radon is 4 days. So I'm just going to put that in. So still on the same question. So we've got half-life of 4 days. And we want to know after 20 days how many atoms have decayed. Now be a little careful here. So far, we calculated how many are left. Okay, now we want to know how many are decayed. So that's quite a different thing. So what we originally had is the number of what's left plus what decayed. And we originally had 40,000, if I'm not mistaken. So I had 40,000 originally. All right, so how do we do this? So let's look at this. We've got 20 days. And one half-life is 4 days. So how many half-lives do you think we have? Got 20 days, one is 4 days. So that's giving us 5 half-lives. Okay, so now we can do what we did before. We can just calculate how many are left. So we know originally there were 4,000 and we had 5 half-lives. So I'm putting that into the exponent. If you want to write it out, you still can. That's absolutely fine. And what we get is 1,250 atoms are left. Okay, so it's important to know what are you calculating. So we originally had 40,000. We now have 1,250 left, plus this number of the decay that we are looking for. So again, just make sure you read the question because we are calculating here how many are left, but that's not what the question asked. So how many are decayed is going to be the original amount minus how many are left. So that's going to give us a 38,750 atoms. All right. By the way, some of you are asking about what radon is. Radon is just an element. And you don't have to know what kind of element it is, or you don't have to know anything about it at all. Take care. Let's see this one. So we've got an original count rate. So remember what count rate was. That was the number of decays per we can have second or minute. Here we've got minutes. And we've got an original count rate of 584 and a final count rate of 73. So this is very similar to the last question of our quiz. So we have an original count rate 584 and that goes to 73. So we want to know how many half-lives is that, right? Because from how many half-lives that is, we can calculate how many half-lives, how many hours one half-life is. So let's do it the same way. We have 584, and if we multiply that by a half, we get 292. So that's one half-life. We go on, we multiply that by a half, and we get 146. So that's 2 half-lives. We still don't have our number, so we go on. 146 times a half, giving us 73, which is 3 half-lives, which is what we want. So we know that 45 hours corresponds to 3 half-lives. And since we want to know how much 1 half-life is, we're going to divide by 3, and we know that 15 hours is 1 half-life, and that's the answer. Okay, so we're going to continue these questions after lunch. We also have some more topics. It's 12:30 now, which means it's lunchtime, so I'm just going to write that on top here. And we've got an hour for lunch. So you guys have a good lunch. And as always, if you have any questions, now is a good time to post them onto the forum, because me and maybe the moderators also will try to answer some of them over lunch. So if you have any questions, just make sure you post them, or we'll have some time towards the end of the session. Okay, so I'll see you in an hour, and have a great lunch. Hi everyone, welcome back from your lunch break. Hope you had a great lunch and that you guys are ready to learn something more about half-lives and then our last topic. So what we were doing before lunch was going through half-life, what it means and how to solve problems on it. So we still have a couple problems to go. So we'll just go through some more past paper problems before starting our final topic. So looking at our next question, we were talking about sodium and we found that its half-life was 15 hours. So I'm just going to write that over here, that our sodium 24 had a half-life of 15 hours. All right, now we're supposed to compare this to something that would have a half-life of 10 years and 10 seconds. And why would sodium be better to trace blood flow? So I'm just going to give you a couple seconds to think about why would a half-life of 15 hours would be better than either 10 years or 10 seconds. So if you have any ideas, let me know in the chat and I'll just go through your ideas. Okay, so we are having something like 10 seconds would be impossible to track or would decay too fast. And for 10 years that it could cause serious damage to the body or it would stay in the body for way too long. And it's not needed. Yes. So absolutely. So looking at the 10 years first, so why is 15 hours better than 10 years? So looking at that, we can basically reach the safe level of radiation faster with the 15 with the sodium. So if we had something that had a half-life of 10 years inside our bodies, then it would have this harmful level of radiation for 10 years, maybe even 20, 40. Whereas if we've got just 15 hours, the sodium will decay fairly fast and we'll reach the safe level of radiation after just a couple of days, maybe in the level of hours. So yes, most of you put in that it would be too much radiation, it would be more harmful, it's not needed to be in the body for 10 years, right? We don't use traces for blood flow for 10 years, we just need maybe some minutes or hours to do that. Compared to it, when we are looking at these 10 seconds, why is 10 seconds too short? So a lot of you are saying it's too short to get any seconds, any result, it will decay really fast, which is pretty much exactly true. So 15 hours can be enough. So it can be long enough to obtain measurements. So 10 seconds means it would decay too fast. So when we get that trace into the body, within 10 seconds, half of it would be gone, which means that trace wouldn't be useful for too long. So that's why the 15 hours would be better than 10 seconds. So thank you everyone for answering. Okay. So for our next question, we've got a rock. So if you guys don't understand some of the words like the igneous rock, that's okay. You don't even need to know anything about these elements like potassium and argon. That's absolutely fine. So we've got a rock that contains this potassium 40. So that's just an element. And this is radioactive. And the important part for us is that it has a half-life of this many years, which is so much. It means it's pretty stable because over 1,000 million years is really, really a lot. And we know that when the potassium decays, it decays into argon. So we basically have potassium and it decays into argon. So it happens, for example, after if I originally have 10 potassium atoms, then after one half-life, half of them decay. So half of them are still there. So I get 5 potassium atoms that stay there. And so these are the ones that stay. And then 5 of them decay, and they decay into this argon. So I get 5 argon atoms. Those are the decayed. So this is what that means. It means that every time potassium decays, it decays into an argon. So we can see that for our sample, let me use a different color. With our sample, we've got 1 atom of potassium for every 3 atoms of argon. So we can say that we've got 1 times potassium, and we've got 3 times argon. Now this doesn't have to be exactly 1 and 3, as long as it's in that ratio. We can have, for example, 5 and 15. It has to be in the ratio though. So altogether, if we've got 1 potassium and 3 argons, that means that we originally had how many potassium atoms? If we now had 1 potassium and 3 argons, then we must have originally had 4 potassium atoms, right? Because we've got 1 plus this 3. So we can see that we originally had 4 potassium atoms and we now have only 1. So that means we only have 1 out of 4 left. Or we can say 1/4 is not decayed yet. All right, so this is a way to think about it. Make sure to write it down like that. If you put in any other numbers but the same ratio, you will still get the same. So here would be 20 into 5 and 15. So you get 5 out of 20 are left. So that's still 1/4. All right, so the answer to that would be that still 1/4 of the potassium atoms have not decayed yet. You can also put in, well, it actually says fraction, so make sure you put in a fraction. Normally you can answer this as a percentage, but if it says a fraction, make sure you leave the fraction. All right, so now we said that 1/4 has not decayed yet. And from that, we're supposed to calculate the age. So how can we use the fraction to calculate the age of the rock? So we've got 1/4 left. After 1 half-life, we have 1/2 of the original ones left. After 2 half-lives, we get 1/4 left because we have 1/2 times 1/2. So that means that if we have a quarter left, 2 half-lives went by. Okay, so we're very close to the time now. We've got 2 half-lives. So 2 half-lives times 1 half-life is this many years. So that together is just 2,600 million years. All right, so in the answer, you've already got the millions, so you just need to put in 2,600 like that, and that's it. All right, so here in this question, we're not really going to go through this part A, so I've kind of completed that for you. It's very similar to that very first question that we did on drawing the graph. And so if you want to, you can go back to that. What I have done here is just plotted all the points that we are given. So I just found 0 and 880, and then 2 and 550 and so on. So just plotted the points. And in part B, we're asked to use the graph to find out how long it takes to go from 880 to 440. So we've got 880 right here. So let's find 440 counts per minute. So we've got 400 here, and we've got 500 just here. So I've got 1, 2, 3, 4, 5 squares in between. So 5 squares is a difference of 100 counts. So each square is 20. So since we want 440, we're going to be looking for this right here. And that looks like this point. So we're going to drop down and see that this belongs to 3 days. So we had 880 at 0, we've got 440 on 3. So we're going to answer 3 days. All right, and since I know a lot of you are usually asking about this, of course, you could put in anything between, I think, 2.8 to 3.2. Okay, some of you are saying you can't see my writing. So let me just reshare this. Okay, it should be okay now. Hopefully you can see it now for anyone who didn't. So anything between 2.8 and 3.2 would be good for an answer to this question. All right, and then for part 2, we're asked what's the half-life of the substance. So I'm actually going to give you a little bit of time to, again, let me know in the chat, what do you think is the right answer to this one? What is the half-life of the substance? And the key here is to remember what actually is half-life. So half-life is the time it takes for half of the nuclei to decay. And we can also see it's also the time it takes for the count rate to decrease by a half. So let me know in the chat if you have any ideas. All right, seen lots of good answers. I'm just going to give it a couple more seconds, see if anyone else wants to give it a guess. All right. So, as many of you said, the answer to that would be 3 days also. And that's because we just calculated that going from 880 counts per minute to 440 counts per minute, which is exactly a half, it takes 3 days, which means that the half-life is 3 days also, right? So this is exactly the same thing. We could also calculate how long it takes to go from 440 to 220, and you would also get that this is, we can see that's from 3 to 6 days. So again, this is 3 days. So it's quite the same thing. All right. For this problem, so I believe that's still question 7. Yes, so this is still question 7. And we are asked, so we've got, there's 3 different isotopes or 3 different elements. And these are just their names. So these are the names of them. And this would be the half-life, and this is the different radiation that's given out. So we are on time equals 0, and we've got the same count rate. So let's put in, for example, 2000 as a count rate, count per minute. All right, so we've got this count rate, and now 1 month from now, so fast forward after 1 month, after 1 month, I want to know which of these isotopes or elements will have the lowest count rate. All right, so which will have the lowest count rate? The way to think about this is we know the count rate decreases after each half-life. Okay, so as it decreases after each half-life, the more half-lives go by, the smaller it will be. So more half-lives means smaller count rate. So in this 1 month, the one isotope or element that goes through the most half-lives is the one that will have the lowest count rate. And I can already see some people answer this question, and you guys are right, as at least from the ones I'm seeing. So yeah, we want something that has the shortest half-life. Because if my half-life is short, let's look at this radon. The radon will go through, let's say, 2 half-life in just a week, whereas this thorium that goes through 1 half-life and a little bit in a month. So this radon will go through the most half-lives in this month. So therefore, it will have the least count rate. So we'll have the radon T as the answer, because it has the shortest half-life. Okay. Now I'll got one more question for you. It has a couple different parts, and we'll be looking at these 3 graphs here. So for the first, we've got 3 graphs, which again has time and count per second or count rate, and we've got J, K, and L. So first thing we want to know is which source has the highest count rate after 24 hours. So what I'm actually going to do is I'm just going to put a J, K, and L into the chat, and you can have a vote in the chat, just like put a, I don't know, what's it called, thumbs up or something on the one that you think has the highest count rate after 24 hours. So I'll give you some time to go through that. Okay, that's looking good. Okay, just going to give you a little bit more time. Okay, I think that looks very much like you guys agree. So I'm just going to get a pen here. So let's look at it after 24 hours. So let's find that time on all of our graphs. So 24 hours could be just about here. So here we've got a count of 20. Here on K, we've got about a 60. And here we've got just about, that's going to be like a 2 or a 4. So that's a 4. So the highest is definitely K. We can see that from the graph that count rate is the highest just from that group. So good job, everyone. And so we had a K here. What about number 2? So you're asked what's the count rate for L after 5 hours. So just going to give you a couple of seconds on that so you can think before I go through. Okay, so we're going to look at L, so that's right here, and looking at 5 hours. So 5 hours going up, and we're just about here in that region. So what we kind of need to know is how much each square is, so because we're not exactly on any line. So we're just about here, I would say. And so each square, let's see, we've got from 40 to 60, we're going in 5 squares. So 5 squares is 40 to 60, that's E20. So each square is going to be E4. So looking at that, we're just about, I would say, 1 square or 1.5 square below the 60. So I would go for a 56 or 54 counts per second. So that's just my estimate. I looked at the answers to that. So the answer would say 56, but anything between 50 and 60 would be accepted for this particular one. So just so you know, put in anything between 50 and 60 is okay. So 52 is fine, 51 is fine. I'm seeing some 54s. So that looks okay. 52 is also fine. So anything in that interval is okay. Okay, thank you for everyone answering in the chat. I love seeing that. Let's see the other part. So now we're looking at which of them has the longest half-life. So I'm going to do that the same way we did part 1. So I'm going to say we've got the longest half-life. And we're looking at J, K, and L. So put that into the published chat and just put a vote on whichever you think has the longest half-life. Okay, you don't seem as sure as before, so I'm going to give it some more time. So I'm just going to say one thing. Oops, let's go back. Just going to say one thing, and that's with having a short half-life is going to mean that the count rate goes down very quickly. That's because it only takes a short amount of time for it to decay from like 100 to 50 or 50 to 25. So short half-life, the count rate goes down quickly, but if we've got a long half-life, it goes down slower. Okay, so I see that most of you agree on one option, which is good, and it's the better thing is it's the right option. So yes, K here would have the longest half-life. So J goes down. If we look at J, it goes down quite fast. We can see after 25 hours, the count rate is only 20, and L goes down even faster. So K only went down to like around 60 after 25 hours. So K has the longest half-life because it goes down the slowest. I also saw a question about what would be K's half-life. And the answer to that, I cannot give you. because we don't have enough data. So imagine this graph, it would continue on. So this curve would go on very, very slowly, but it would go on like that. So you can imagine it has to reach 50, which is just about here. So it would most probably be about maybe 50 or even over 50 hours. It would be pretty long. So you would have to have a way longer graph than this. So it only reached around 60. So you would need to go on and on. I would think it could be around 70 hours, but we can't say. Okay, last part of this is, so we've got a source. So this is not related to the graphs anymore. We've got a source that has a half-life of 6 hours. And we've got 3 options. And we can either use this to measure the thickness of paper as it's made in a factory. We can use it as a medical tracer, or we can use it as a smoke alarm. So what are these 3? I'm going to do it by the poll again. You guys seem to engage with that, which is nice. So I'm just putting in thickness of paper for that option, and then medical tracer or smoke alarm. So any of these, what do you think is the best way to use it? You don't need to worry about how it works. So you don't need to know that we use alpha particles for smoke alarm, or how is thickness of paper monitored. You don't need to know how it works. Just think about the half-life itself. Also, I would very kindly ask the person who's putting random messages to stop so that other people can actually ask questions. That would be great. Okay, just giving you a couple more seconds, but you again seem to kind of agree, which is nice. All right, and I'm going to give it away saying that you all are right. So it is indeed the medical tracer. Why is that so? So both the thickness of paper and the smoke alarm are kind of like long-term things, right? So we need, for both of these, we would want this source to quote unquote work for a long-term period of time. So imagine you would install a smoke alarm and the radioactive source would only have a half-life of 6 hours. So your smoke alarm would only work for, let's say, 6 or maybe 12 or 18 hours. Because after each half-life, there would be less and less of it. So after just 18 hours, there's only 1/8 of it. So it wouldn't work too great. Same goes for thickness of paper made in a factory. So again, I assume you wouldn't want your factory or the thickness of it, the monitoring of the thickness work for like, let's say 18 to 24 hours. We want it to work for days and years, right? So that wouldn't be too good because you would need to change the radioactive source very, very often. So the last option is the medical tracer, which we talked about before, which is a good option because the 6 hours allow us to get results. But the dangerous amount of radiation is not in the body for too long. So we reach safe amount of radiation let's say fast enough, so it's not in the body for too long. So you, of course, don't need to put in your reason, but these would be the thoughts that should be going through your head. All right, so these will be all the questions that we're going to go through the half-life. We now have one more topic to go through, so we're going to dive right into that. And this topic is nuclear fission and nuclear fusion. So before that picture gives it away a little bit, but before I dive into it myself, I want you to let me know in the chat if you've heard about nuclear fission or fusion before, and if yes, what are some things that come to your mind when you hear it? Also, someone's asking what's a tracer. So a tracer is like an object that you would put in your body, and it would go through the body. For example, to show the blood work, you could, it would, as it goes through the body, wherever your blood goes, you can see exactly where it is. So that's kind of a short way to explain what a tracer is. Okay, a couple of you have a nice idea of what nuclear fission or nuclear fusion is. I'm just going to close the chat for a little bit now. So the basic idea, as many of you are putting in, is that nuclear fission is splitting one big nucleus into smaller ones. So we've got big nucleus into smaller ones, whereas having nuclear fusion means having smaller nuclei being connected into a bigger one. So each has a different use, and each is a little bit of a different process. It's pretty much the opposite, but the basic is that with both of these, some energy is released. So that's the main reason we use them. And of course, they can also be misused. So talking about nuclear fission then, we have a large nucleus that is unstable. So for this, you usually use uranium or plutonium. In nuclear power plants, it would usually be the uranium, and the nuclear weapons, you would also see plutonium. And since it can happen that this unstable nucleus spontaneously decays, it's usually the alpha or beta decay. It's not quite the fission that happens spontaneously. So we kind of help it and encourage that by pushing a neutron against it. So we've got this is our big unstable nucleus. And this yellow thing is a neutron. So when we found out that when we send a neutron against this nucleus, what happens is that it decays into two smaller nuclei, and we get more neutrons. And then what happens that each of these neutrons again bumps into a bigger nucleus, and that again is split into two smaller ones and some more neutrons, and this goes on and on. So with each fission we get more neutrons. So this happens more and more, and it can actually become uncontrollable, which is what happens in the nuclear weapons. As I mentioned, uranium is usually used in a nuclear reactor. We're told here due to the uranium-235. I don't think you need this for GCSE, but it's a nice little fact to know. It's good to remember that uranium is used in nuclear reactors. So the reason we put in this nucleus is because this a neutron is because as it goes there, our nucleus becomes even more unstable. So as we said, what happens is it becomes two smaller nuclei, 1, 2, and we also get 2 more neutrons. And we get some gamma radiation. And what we found, and that's the most important part why we do this, is that we get energy. So energy is released. So with these 2 new nuclei and these neutrons, we also get energy. And that's very important because this energy is then used to generate heat, and then that drives the turbine, and that heats up water, and then this water then drives another turbine, and that all gets into a generator. So you don't quite need to know about this part, what happens afterwards, and how exactly each nuclear power plant works. But you should know that the energy is important. This energy is then used to generate electricity. And there's a little black box that goes from the energy to electricity. So you don't need to know what happens there. Okay. So as I mentioned, as each of the new reactions introduces more and more neutrons, it means that this reaction can go on forever, and it actually multiplies and gets bigger and bigger with each new reaction. And we call this a chain reaction. And this has to be moderated in a way. We use control rods in nuclear power plants to control and kind of slow down these neutrons so we wouldn't get so many of them. So we would put in so-called control rods, and we would get rid of some of the neutrons because there would be too many of them, and this fission could get out of control. However, of course, for people who wanted to use nuclear fission as a nuclear weapon, what happened was they didn't put in these rods, of course, and they wanted for the fission to get out of hand. So no control here, which means with every new reaction, the number of following reaction would be doubled, and the effect would be disastrous, as we all know, if we know anything about the previously used nuclear bombs. So it's really important for this not to happen by accident, and that's why we have these control rods. Some of the materials that we use for control rods are boron or hafnium. Again, just a little fun fact that you don't need to remember by heart, strictly speaking. All right. As I said, controlling the chain reaction and stopping the chain reaction is really important. And there were 2 instances where this didn't happen, and when the reaction got out of hand. And one of them was in Chernobyl, and then another one was Fukushima. which you have most likely heard these names before because they're very, very well known. Both were one of the worst nuclear disasters in history. There was a lot of radioactive material scattered across a vast region around these power plants, and of course, lots of injuries and deaths kind of connected to it, which is one of the reasons why many people are against nuclear power. However, it's these disasters that really lead to very, very high safety standards in nuclear power plants. They have to be checked very, very frequently, as we saw that they were design flaws before, and also the people working there would have to go through given exams and examinations very often to make sure they know what to do in what scenarios, so they could do everything to stop another disaster like that happening. But Chernobyl and Fukushima were some of the ones that we unfortunately didn't stop, and they're one of the worst disasters. All right. So that was fission. So again, nuclear fission would be used in nuclear reactors for power plants, or it can also be misused for nuclear bombs and nuclear weapons. On the other hand, nuclear fission, as we have established, is taking two smaller nuclei and connecting them to a bigger one. So it's kind of like the opposite. So smaller, lighter nuclei are joined together. And one of the ways that this can happen is if we have 4 hydrogen nuclei. So hydrogen is just an H11, so it's just 1 proton. So we'll have 4 hydrogen nuclei coming together in a reaction. And of course, for helium, we'll also need we'll also need, there'll be a reaction going on. So we'll get a helium nucleus. So this is going to be helium, and these are 4 times hydrogen. All right, so there's an inside reaction there. And this reaction is exactly what happens on the sun. So in the surface or inside the sun, so it's a giant, practically burning ball, you would have lots of hydrogen, and these hydrogen nuclei would come together and they would create more helium nuclei. So the sun is actually very, very large fusion generator. We're trying to find something similar on Earth, actually, because we found out that this is actually really efficient, and we found out that energy is also released. Okay, here's a little detail of what this looks like. So what happens on the sun exactly when we go into details is that we've got so-called deuterium. So this is a hydrogen isotope. We have a special name for it. And tritium is another hydrogen isotope. Again, we've got a special name for it. So deuterium has 1 proton and 1 neutron, whereas tritium has 1 proton and 2 neutrons. They're just different isotopes. And now when they come together, that's called fusion. And what we get from it is a helium, a neutron, and energy. And again, this energy is what we as humans are interested in. So what we have, of course, tried is to build our own fusion reactors. However, we know that all nuclei are positive because we know in nuclei that's protons and neutrons. And protons are positive. And we know when we have the same charges, right, like plus and plus, they repel each other. And that force is actually quite a strong thing. So we have to overcome this repulsion between them. So that means that our particles our nuclei have to travel really, really fast. So right here, we have to be really, really fast to actually get them to collide. Because normally if you push them together, they kind of sense the presence. They sense the presence of each other and they try to go the other way. So if you push them against each other really, really fast, they don't have the time to be pushed away. You can imagine magnets kind of under this also. So they have to be really, really fast. And for them to travel really fast, the temperature has to be really high. All right, so fast means hot. And it has to be so hot that it has to be very, very hot gas or plasma. So plasma at very high temperatures. So what we kind of are trying to do is to recreate our own little sun, right? We're trying to get our little nuclei to be so hot or get into a plasma just like it is on the sun, which of course is quite difficult. So here we've got the temperature that would be needed for fusion to actually occur, which, just look at that number, it's huge. All right, so just to mention, on the sun, we talked about hydrogen and helium, and from this we get energy. And then this energy can also be used to get more heavy elements. So as we get from helium, maybe we even get to carbon and oxygen and iron. So these are just names of other elements that are bigger. So heavier is going to mean bigger. And this can only happen with some older stars and some heavier stars. All right. So as I mentioned, we try to create our little suns to get some nuclear fusion as a source of energy, but it's very, very difficult to actually retain that high temperature. So basically we need high temperature or fusion. And it actually costs energy to get high temperature, right? We need energy to create high temperature, and then we get some energy from the fusion. So the state this is in at the moment is that this energy that we need to just run that generator is higher than the energy that we get. So it's quite inefficient because, for example, if you put in, I don't know, 2 megajoules of energy to have it run, you maybe get just like 500 joules that you get from the fusion. So of course it doesn't make sense to run it because it costs more energy than you get out of it. However, it's actually a really big topic in science at the moment. There are multiple places where they're trying to get this to work. I know one is in France, and they're actually very close to like having these 2 energies the same. So at least kind of balancing these energies out and maybe even getting some energy out of this. If that's a topic that you're interested in, you can of course Google it after our lesson. So this might actually be the future of our energy. So these generators are being researched at the moment all over the world, and I think France is one of the countries that is coming quite close in one of their projects. All right, so 2 things that we covered here were nuclear fusion and fission. So important things to remember is that for the fission, we've got one big unstable nucleus. And to that, to make it even more unstable, we add a neutron. And when we do that, we get 2 smaller nuclei, and we get more neutrons. And since each of these new neutrons, each of them contributes to a new reaction, the number of reaction is exponentially growing. And because it's exponentially growing, there are 2 options. It can be either misused, meaning nuclear weapons, or it can be controlled by so-called control rods. And this is then used in nuclear power plants. Okay, and so these are the 2 actually also places that we would use nuclear fission, nuclear weapons, nuclear power plants. Thankfully, the second one is more often used. So that's that. And then for nuclear fusion, we get 2 or more smaller nuclei, and they come together to form a big one, plus sometimes maybe some neutrons or so. The important part about this is here we get some energy, and here we also actually get some energy. So that's the primary reason why we do all this. And our little where we see fusion and where we came to see that it can be good to use for energy generation is the sun. So the sun is actually a huge fusion generator. So it uses hydrogen to get helium. We can also get oxygen from there. We can also get carbon or even iron. And not all of this happens in our current sun, but big stars, or all the stars can produce these heavier elements. And by heavier, we mean the larger. Okay, so these would be some things to know. The sun was where we spotted that. At the moment, we try to create something similar. Right? And some of the reasons that why we haven't done that yet is because we've got, it's all about nuclei, right? It's called nuclear. So nuclei are positively charged. That means that they repel each other. And that means we need high temperatures for them to move very fast. Because when they move very fast, they don't have time to repel each other and they just move. And they can come together and fuse into this bigger element. So the reason why we haven't done this, as I said, why this isn't working yet, is because this high temperature, we need lots of energy. Oops. Lots of energy needed. And this energy is bigger than the energy generated as of now. Maybe if you're going to be talking about the same topic in a couple of years, we'll actually have some fusion reactors. All right, so that's a little overview. What we have now is a couple of questions from past papers about this. So we're going to go right into that. And I'm going to give you a couple of seconds to think about this one. If you want to get right into the chat, you don't have to. So just think about some differences between fusion and fission. Okay, so just giving you a little bit of time. We have practically talked about this big difference between them quite many times today. So just going to see what some of you are saying. Okay. Yes. All right. Got some nice answers in. And so the largest difference between the two would be that for fission, so right over here, we are splitting a nucleus. We can say the nucleus is unstable. We can mention it is big. Whereas looking at fission on the other hand, we are joining nuclei together. So, and we're joining them. We can also put in that they form a larger nucleus. So it's pretty much up to you how much detail you put in, but it's very important to mention that the first one, fission, is splitting of one nucleus, whereas in a fusion, we're joining the nuclei. And then for the second part of the question is what's released during both of these processes. So just a little hint there, I mentioned that that's the most important reason why humans are actually interested in these processes, of course, kind of selfishly, but it's one of the main reasons why we're interested. So again, just going to give you a little bit of time to think about that. Okay, so you are on the right track, absolutely. All right, love seeing that. So yes, during both fission and fusion, the reason we're interested in this is that energy is released. It happens that it's released by both, even when we put them together, and even when we tear one nucleus apart, energy is released in both of these. Okay. Now, another thing that I just mentioned as a little fact is that plutonium is one of the materials that can be used in nuclear reactors. So one of the other very well-known elements is used as fuel. So again, just giving you a couple seconds to think about what is another element that's usually used in nuclear reactors. So let me know what you think. Giving that one just a couple seconds. Hi, amazing. So many of you are getting that right. All right, yes, so let me just grab a pen. So the one that you guys use the most is uranium. So definitely uranium, most often this would be uranium-235. You could see 238, I suppose, but uranium-235 is the other most well-known substance to be used. Not sure if some of you have maybe mentioned thorium. So that's also an option. If any of you are really into this, then also so-called mixed oxides, which we write as MOX, can be used in a way, but uranium is the most well-known on this one. Okay. And we're now back to atoms and elements and isotopes. So this is the last question of today. I'll give you guys a little break afterwards, so stay on here to answer this one. So we've got plutonium, which is an element. And we've got different isotopes. So my question is here, what are isotopes? What do they have in common, or what's the difference? So we know that atoms that have same number of protons we call this the atomic number that these atoms are of the same element. So now what's the difference between an element itself and an isotope of an element? Just going to see. What are some of you saying? Hi, good, good. Okay, I love to see that you remember what are isotopes. So yes, isotopes. My pen's probably gone. Isotopes are of the same element. So isotopes are same element. That means they have the same number of protons or the same atomic number, but we've got a little or a big but here. They have, excuse me, they have a different mass number, meaning they have a different number of neutrons. Oops. All right. So this question actually asks only what they have in common. So when we look at these, what they have in common, what's different, they have the same number of protons or the same atomic number. So if you have said anything like that, that's the right answer. And they have a different number of neutrons. So the answer to this would be same number of protons or same atomic number. Doesn't matter which one you use, both are fine. Okay, so here we come to the end of the questions today and of the material that I wanted to go through. So I want to give you a little break, and after that we'll have some question and answer time. So we'll have a chat opened and I'll just go and try to see if you want me to go through anything again, if you have any further questions, and I'll try to answer as many as possible. So over the break, you can think of some questions that you had. So it's T43 now, so just going to give it 5 minutes. And let's be back at that time to talk about some questions that you guys might have. All right, I'll see you in 5. you need to find it. All right, sorry. Hopefully you can hear me now. So what you need to do here. All right, hopefully you heard me at least for a little bit. Okay. So if you need to find a half-life, I'm just going to go through that left part again in a little bit. If you need to find the half-life, then first thing first, you need to find the number of half-lives again. And so we had 40,000 and now we have 5. So we originally had 40,000. So after one half-life, that's 20,000. Right? After 2 half-lives, that's 10,000. And after 3 half-lives, again, only half are going to be left. So that's 5,000. And that's the number that we want. So that's actually what we're looking for. So we've got a number of half-lives, and then we need to find length, let's say, of the half-life. So we know that 24 hours went by. So 24 hours are 3 half-lives. So just from that, if you want to know what's one half-life, then 8 hours is one half-life, and that's the answer. Okay, so these are the 2 types of questions. I'm just going to go back quickly. Sorry, I didn't see that I was muted. So for this left part, this is the other type of a question that you might get. And it's that you'll get the number of half-lives, or you need to calculate it. So for example, if you know a half-life is 5 days, you're interested in 10 days, make sure you always convert it to half-lives. So we do that, and then you would use this here to find the final number of atoms left, or nuclei left, or whatever the question is asking about. So here, if we originally have 20,000 and we've got 2 half-lives, we just plug that in, and after 2 half-lives, we've got 5,000 atoms left. So hopefully that makes sense. And another question that was asked quite a lot were the nuclear equations. So here for the nuclear equations, you basically want the numbers on the left-hand side being equal to numbers on the right-hand side, obviously, because it's an equation, so that's what we do with equations. So that's one thing to remember. And then when we're looking at any element, the number on top is the mass number, and the number of bottom is the atomic number. Right, so we want the numbers on the top to be equal to the numbers on the right-hand side and top. So what you need to remember is that the alpha particle has a 4 and a 2. You can write it as an alpha or as a helium. That's up to you. And then you need to remember that beta has a 0 and -1, or you can write that as an electron, 0 and -1. This is the info that you need. So let's try that out. If I have a uranium 238 and 92 that undergoes alpha decay, and I get this element here, I'm interested in the numbers in the element. And then let's do the same thing on the beta decay. So the way you'd go about this is you fill in your numbers on the alpha, and then you just use that as an equation. So 238 plus 4, equals, there's an equal sign over the arrow, is equal to 4 plus something. So that needs to be 234. And then on the bottom, we will get 92 is equal to 2 plus 90, right? So I just add in the numbers so that they will make sense. And the same is what you would get for your beta. You get a -1 and 0. And exactly the same process, all right? 238 is 0 plus 238, exactly the same. And then on the bottom, we've got 92 is -1 plus, and be careful with this -1, right? It's a minus. So this is 93. And that's pretty much it. All right. I'm just going to go very quickly through the chat. I'm sorry if I didn't get to your question. Someone thought it was really great to spam, so I don't get to see lots of the questions through the spam. So also sorry about the muted. All right. So if you have any last minute questions, let me know so I can answer that. I know we lost some time with the mic not being on. All right. How do you motivate yourself to study? Give yourself breaks and snacks. My go-to thing is a snack. So just promise yourself to maybe be very specific. Like you will say how many problems you'll go through or how many chapters you'll go through, and promise yourself as a reward. We as people work wonderfully with rewards. So just promise yourself a reward, and that actually helps. All right. It doesn't seem that you guys have any burning questions otherwise. So if yes, I hope the moderators were able to ask them, and you can always watch the recording again or refer to my presentation. All right. Okay, so everyone have a great Sunday. I hope you had a great weekend. Thank you for coming here to learn with me, and hope to see you all next month. All right, see you soon.